Okay, so just resuming what we have just with the test 3 review, and we have with question number 12 from the packet. Okay, and it says to use the factor theorem to determine whether x plus 3 is a factor of p of x is equal to x cubed plus 4x squared minus 9. Okay, so for what we have in the case of number 12, okay, so we have you have the divisor, okay, to be at x plus 3. And if I set things up along the lines of polynomial division, and we'll start out in the format of line division, but we're going to use synthetic division to solve. Okay, so you got the dividend, again, at x cubed plus 4x squared minus 9. Okay, so you have x cubed, and we have plus 4x squared. And we do not have a first order x term, so we're going to have using 0 for placeholder purposes. Okay, so you have 0x, and we have minus 9. Okay, and just translating what we have in the context of synthetic division. Okay, so we have for the divisor x plus 3. Okay, we're going to attain the 0 of this, for which we're going to have negative 3. And so for what we will have here, and translating in the context of synthetic division, okay, and what I'm going to do here is that I normally like to have the elbow formation as the partition for negative 3, but I know in ALEKS it kind of has the old traditional division set up here. And so just isolating negative 3 still. Okay, so you have with the coefficients of the dividend. So you have 1 for x cubed, 4 for x squared, and you have 0 for the missing x term. And again, we want the dividend to close out with a constant, which we have at negative 9. And initiating the synthetic division case, so we have with the first coefficient, which we have at 1. We bring this down, then we have negative 3 times 1 is negative 3. 4 plus negative 3 is 1. Negative 3 times 1 is negative 3. And we have 0 plus negative 3 is negative 3. And negative 3 times negative 3 is a positive 9. Negative 9 plus 9 is 0. So for what we have here, okay, we have the remainder is going to be equal to, okay, and we had the polynomial in terms of p of x, and the remainder is going to be p of the 0, which we have at negative 3. And that is equal to 0. And so for what we have here, okay, so you have in the layout, okay, so we're going to have that p of negative 3 is equal to 0. And if the remainder is 0, then the divisor is a factor. If it happened to be non-zero, then it would not be a factor. But since we have 0, this signals that x plus 3 is indeed a factor. All right, now looking at what we have in dealing with asymptotes, and we have two rational functions with f of x and h of x, and we have graphs on display, and we're looking at which of the graphs will come closest to matching f of x, and then we're looking at the graph that will come the closest to matching h of x. And we have for the first part here, okay, so we have for f of x is equal to 3x plus 6 all over x squared plus 2x minus 8. Okay, now we're going to look for the asymptotes. Okay, and we have, first of all, okay, we have for 3x plus 6 over x squared plus 2x minus 8. Now if I factor, you have 3 times the quantity of x plus 2. And we have for x squared plus 2x minus 8, we have with the factors, okay, we have x plus 4 and x minus 2. Notice that there is no cancellation of the denominator expression, so the zeros of the denominator factors will be vertical asymptotes. Okay, and I'm not drawing out the restricted values from the domain. Okay, I'm just going ahead and tackling the vertical asymptotes. So you have x plus 4 equal to 0, and we have x equal to negative 4, and we have x equal to 2. So those are your restricted values from the domain, and the zeros of the denominator factors. Okay, those are going to be the vertical asymptotes, where we have x equal to negative 4, as well as x is equal to 2. So you've got two vertical asymptotes, and for any other asymptote that we have regarding this particular function, okay, so you have 3x plus 6 all over x squared plus 2x minus 8. And for the comparison of degrees, okay, so x and 3x is going to be a first order, so we have that n is equal to 1. Highest order term in the denominator, we have an x squared, so we have that m is equal to 2. And we have in the comparisons, okay, so we have that n is less than m. And so there's going to be a horizontal asymptote. And when the degree in the numerator is less than what is in the denominator, can we have that the horizontal asymptote is going to be the x-axis, namely y is equal to 0. So we've got these three asymptotes, and to see which of the graphs will have these asymptotes, so we have x at negative 4 as well as 2. And if you notice, okay, we don't have this present in graph A. We got x equal to negative 4, x equal to 2, y is equal to 0, so B is still in the running. And C is also in the running. And you got negative 4, 2, horizontal asymptote, so D is in the running. Now we don't have the same vertical asymptotes in graph E. And we have different vertical asymptotes also in graph F. Okay, so you have possibilities here with graphs B, C, and D. And in terms of what's going to be the tiebreaker, okay, so all these had the same asymptotes, and the tiebreaker very likely is going to come with the determination of the y-intercept. So with the y-intercept, okay, so you have the ordered pair, okay, we have at 0y, and for this particular function, okay, we have y is equal to f of 0, and we have 3 times 0 plus 6, and we have all over 0 squared plus 2 times 0 minus 8, and so we have 6 over negative 8, and that is reducible to negative 3/4. So your y-intercept, you have a y is equal to negative 3/4, or in coordinate terms, we will have 0, negative 3/4. Okay, and seeing which of the graphs will have 0, negative 3/4. And if you notice in graph B, we have a positive y-intercept on the y-axis, so it's not going to be B. C has a positive y-intercept when it needs to be a negative, if it's to match graph F. And for graph D, okay, notice we have the y-intercept on the y-axis. You have right very close to negative 1, so you have 0, negative 3/4, so you have in close proximity. So for the question, which of the graphs will come the closest to matching f of x, and the result here is going to be graph D. All right, now in the case of h of x, okay, so hitting the reset button, and we have h of x, you have 8 over x squared minus 2x minus 3, And if I go ahead and write this out in factored form, okay, so we have with x squared minus 2x minus 3. So the binomial factors, we're going to have x plus 1 and x minus 3. If you notice, there's no cancellation whatsoever. And we can say that with the zeros of x equal to 1 and x minus 3. Since those factors remain, the zeros will come to define the vertical asymptotes. In this case, from x plus 1, we have x equal to negative 1. And with x minus 3, we have x equal to 3. And in terms of any other asymptote, to add to the vertical asymptotes. Okay, and we have with the degree comparison. Okay, so we have in the numerator. Okay, we have n is equal to 0. Okay, since again there is no x term that is present. And we have in the denominator. Okay, we have the degree to be at 2. And we have a bit of partial history to repeat. For once again, the degree of the numerator is less than what is in the denominator. And so once again, we're going to have a horizontal asymptote. Y is equal to 0. Okay, so you got, for the vertical asymptotes, we have x equal to negative 1, x equal to 3. And again, we have the horizontal asymptote to be y is equal to 0, or namely the x-axis. So looking at what we have here, so we got negative 1, 3 for A. Okay. B, we don't have the match. C does not match. And we have D, doesn't match either. And so it turns out for E and F, okay, we got the same asymptotes, okay, vertical and horizontal. So it comes down to one of the graphs A, E, and F. And the tiebreaker, okay, is going to be once again with the y-intercept. So for the y-intercept, okay, you have the determination of y whenever x is set to 0. Okay, so we have 8 over, you can have 0 squared minus 2 times 0 minus 3. And guess what? We have 8 over negative 3. So we have that y is equal to negative 8/3. And so we're going to have, for the y-intercept, we're going to have almost negative 3 as the location of the point on the y-axis. And so just looking at what we have in the running. Okay, so we have for graph A, okay, so you have negative 2, between negative 2 and negative 3. That looks good. Graph E, okay, the y-intercept is positive, so that goes out. And for graph F, okay, the y-intercept is positive when it needs to be negative, so that goes out. And so only A remains. Okay, so for the graph of h of x, that which will best match is going to be graph A. Now, for what we have in the case of item 14, and we have again another pair of rational functions, and we have f of x is equal to 2x squared plus 2 all over x squared minus 2x minus 3. And if I go ahead and factor this out, okay, so 2x squared plus 2 all over x squared minus 2x minus 3. Now in the numerator, okay, we have 2 is the common factor. So we have 2 times, okay, the quantity of x squared plus 1 in the denominator. Okay, so we're going to have x plus 1 and x minus 3. Once again, okay, so So we have no shared factors between the numerator and denominator. So x plus 1 and x minus 3 will remain. And the zeros from the denominator factors are going to turn into the vertical asymptotes. So for x plus 1, we're going to have the vertical asymptote x is equal to -1. And for x minus 3, again, we're going to have x equal to 3. And in the case of any other asymptote, okay, so this will come down to degree comparisons between the numerator and denominator. Okay, so we have in the numerator, okay, we have the square in 2x squared. So the degree of the numerator is going to be at 2. And for what we have in the denominator, okay, we'll have the m is equal to 2. Okay, now we have that n is equal to m. And so we now have still another horizontal asymptote, but it is going to be non-negligible. And so we're going to have y is going to be the constant formed as we take the ratio of the highest degree terms from the numerator and denominator. So we have 2x squared over x squared. So we got a 2-to-1 ratio, so we have that y is equal to 2. So we got these three asymptotes. Okay, so we have and 14. So you have x at -1, 3, y equal to 2. So a is in the running. In the case of graph B, okay, we've got the horizontal asymptote, but we have x equal to -2 when it needs to be -1, so that will go out. C, okay, we don't have the perfect match in the asymptotes. And D, no. And we've got x equal to -2 and 3. Okay, so we don't have the x equal to -1 in graph E, but we do have x equal to -1, x equal to 3, and y equal to 2 present in both graphs A and F. So it's going to come down to either one of these, and it looks like we're going to have the tiebreaker to be what the y-intercept turns out to be. Okay, so if you notice in A, the y-intercept is positive, whereas in F, okay, it is going to be negative. Okay, so for the y-intercept, okay, so you have the y, again, so you have equal to 2 times 0 squared plus 2, and that's going to be your f of 0. Okay, you have all over 0 squared minus 2 times 0 minus 3, and if you saw the result already, that's fine, because you have 2 over -3. So y is going to be at -2/3. So your y-intercept is going to be at 0, -2/3, and between the graphs, okay, so you have y equal to -2/3 on the y-axis at graph F, then in A, again, the y-intercept is positive, which it cannot be, in order to define what we have for the function f of x. So out of these possibilities, only graph F is going to match what we have required for f of x. And in the case of g of x, now we have 2x minus 2 all over x squared minus x minus 6. Okay. And for what we have in the case of g of x, okay, now I'll go ahead and factor this on out. Okay, so we have 2 times the quantity of x minus 1, and we have all over, okay, we have x plus 2 times the quantity of x minus 3, okay, and so we don't have any shared factors, so the denominator expression is x plus 2 and x minus 3 will remain, and since they remain, the zeros of these, okay, have the restricted values from the domain, and they will come to define the vertical asymptotes, okay, where we have x equal to -2 and also x is equal to 3. And in terms of any other asymptote, okay, so we're going to have the numerator degree is going to be at 1, and for what we have in the denominator, okay, that's going to be second order. Okay, and so we're back to where we have the degree of the numerator to be less than what is in the denominator. Okay, and so we have here, once again, we have the horizontal asymptote is going to be at y is equal to 0. And so just looking at what we have in the lineup. Okay, so you have -2, 3, but we don't have the right horizontal asymptote for graph A. We got -2, 3, but the wrong horizontal asymptote. C, that also strikes out. D, we have -2, 3, and we got the right horizontal asymptote. We got -2, 3, and the right horizontal asymptote. And graph F, no. Okay, so it comes down to what we have between graphs D and E. Now D has just a positive value for the y amounts in the y-intercept, whereas in E, okay, this is going to be negative. So the tiebreaker again is going to come down to the sign value of the y-intercept. Okay, so we have for the y-intercept, okay, and so we have y, okay, so we have g of 0. Okay, so we have 2 times 0 minus 2, and we have all over 0 squared minus 0 minus 6, and we have -2 over -6, and so that will come down to positive 1/3. Okay, so we have for the y-intercept, okay, so you have a positive value in y. Okay, so the y-intercept is positive in D, but it is negative in E. And so the best match among these graphs is going to be D. Yeah, and so that'll be that which best applies to what we have for the function laid out for g of x is equal to 2x minus 2 all over x squared minus x minus 6. Now, looking ahead, now we have with the added test review items, and I sent that out the other day, and we have going back to quadratic functions, okay, and we have again we have in the case of item 1, okay, and it's asking, okay, does the function have a minimum or maximum value? Okay, this is not a yes or no question, and for what we have in the case of the first item, okay, so we got the standard form of this particular quadratic function, and I'm going to translate what I have here along the lines of the vertex form. Okay, so if we start out separating the variable terms apart from the constant, okay, so we have negative 3x squared minus 12x. We can go ahead and group together in parentheses and just have the 17 outside and following. And again, in the setup for the completion of the square, which is one of the initial pathways to the vertex form, I want the first term in the parentheses to be x squared. And since I have the leading coefficient to be -3, I can just factor out the -3 from the parentheses. So -3 into -3, x squared, that would be x to the second. Negative 3 into negative 12x is going to be a positive 4x. Again, we have followed by the addition of 17, and you can double check. You got negative 3x squared, negative 3 times 4x, negative 12x, and we have plus 17. Okay, so we have the conditions where we can initiate the completion of the square. And this will be done by taking half of the coefficient alongside the first order variable x. Okay, so we have got half of 4, and then after taking half, okay, we're going to square. Half of 4 is 2, and 2 squared is equal to 4. And that number which we squared, namely 2, is going to re-enter the scene once we get to the vertex form. Okay, so for what we have in the process, okay, so we got f of x is equal to negative 3, and we have times the quantity of x squared plus 4x. You have plus 4. You have plus 17. And now for what we have initially, we have a bit of an imbalance created, because once I add 4, okay, this would become like negative 12 plus 17, so that would be a positive 5, and I want to get it back up to 17. And so for what is happening is that as 4 is added within the parentheses, I'm actually adding negative 3 times 4 at the front, so I'm creating a deficit in the amount of negative 12. And to override this deficit, I'm going to add 12 to 17. And so we will have in the rewrite, okay, we have f of x is equal to negative 3 times quantity. So we have x squared plus 4x plus 4 plus 29. And again, I can check to see if this goes back, or this can be converted back to the standard form. Okay, so again, we have negative 3x squared, negative 3 times 4x, negative 12x, negative 3 times 4 is negative 12, negative 12 plus 29 comes back to 17. And so we're going to have for the vertex form, okay, so we have f of x is equal to negative 3, and we have times the quantity. Okay, now for x squared we have x, and again, how I formed this trinomial originated from developing 4 upon squaring out positive 2, and again, the 2 is going to reappear in the vertex form. So we're going to have negative 3 times the quantity of x plus 2 to the second, and we have followed by the addition once again of 29. Okay, and so we have in this particular case, right, so we have with a, h, and k, so you have the a is equal to negative 3, and since a is negative, okay, f of x is going to open down from the vertex. So that means that the vertex is going to be the high point. So that would be the location of the maximum. And for the coordinates of the vertex, okay, so if x plus 2 is equal to 0, well, your corresponding h value is going to be the 0 of x plus 2. In this case, you have h is equal to x is equal to negative 2. And for the 29 at the end, okay, we have that k is equal to 29. And so we're going to have for the vertex, so the vertex hk is going to be at negative 2, 29. Okay, And so just for this problem, okay, going back to the portions here. Okay, so we have, again, does the function have minimum or maximum value? Again, because the graph is opening downward, okay, the vertex will be the peak point. So it's going to have a maximum. And again, in terms of where the minimum or maximum value occurs, and that is going to be the x or h value. So that's going to be at -2. Okay, so I have a -2. And for the maximum value, that's going to be your y or k value. And so this will end up at 29. Okay, and so we have in the setup. Okay. I think I still got this. Let's see. Yes. Okay, so we have for this function, okay, so you have -3x squared minus 12x plus 17. And again, -2, 29, the vertex, that is going to be the top point in the graph of this function. All right, now for what we have in the case of the next set of items, and we have for number 2, okay, we have a function that is provided in factored form, and we're looking at end behavior, zeros, multiplicities, y-intercept, and the graph. Okay, so again, we have f of x is equal to 3x squared. We have times the quantity of x plus 5 times 3 minus 2x. Okay, again, we have raised to the third power . Okay, now for the end behavior, again, this is going to be contingent upon the highest degree term is going to be, and as well as the characteristics, what the sign value of the leading coefficient is going to be, as well as the degree of the function. Okay, so we have for this one, okay, for this particular function, okay, so looking for the highest order term. Okay, so we have with our factors here, we have at the front, we have 3x squared. So this is just a monomial term. So in its own entity, it is its own highest order term. Now for x plus 5, between the two, okay, we have higher order in x with x. Now we have a 3 minus 2x. The higher order term in x is going to be -2x. And since we had the cube of this factor, we had the formation of the highest order term to involve taking the cube of -2x. So we have with the highest degree term, okay, so you got 3x squared from the first factor, and from x plus 5, again, the higher order term we have at x, and from 3 minus 2x raised to the third. Okay, we have -2x is a higher order term, and then we have raised to the third. And so we have in following through, and we still got 3x squared times x, and if I cube out -2x, -2 cubed is going to be -8, and x cubed is going to be x to the third. Okay. And so for the highest order term, okay, we've got 3 times -8, which would be -24. X squared times x is x cubed, and then multiplying by x cubed, this will come out to x to the 6th. Okay, and so we have with the characteristics of the highest order term. Okay, so you have a of n is equal to negative 24 so that is negative, and for what we have in the case of n, okay, we have n is equal to 6, which is even. Okay, so you have a of n is negative, and we have that n is even. And so for the end behavior, okay, since we have an even powered function, it's either going to be opening, or I should say moving up on both sides, or moving down at both ends. And with the sign value, the leading term being negative, okay, that means it's going to fall to the left and fall to the right, or down to the left, down to the right. Okay, so it's going to be moving downward at both ends. And we have, in the case of the zeros and the multiplicities, so that was the result for part A, falls to the left and falls to the right. Okay, now, in the case of what we have with part B, okay, so looking for the zeros. Now we got 3 distinct factors. Now for 3x squared equal to 0. Okay, so if I divide by 3, I have x squared equal to 0. And we have with the square root property of equality. Okay, so 0 is not going to be positive or negative, it's just going to be 0. And for x plus 5, for x plus 5 equal to 0, okay, so we have that x is equal to negative 5. And for 3 minus 2x to the third, okay, so we have with 3 minus 2x equal to 0, so we have negative 2x is equal to negative 3. And with division by negative 2, you can say that x is equal to 3 halves or 1.5. And okay, so we have, again, 3 distinct zeros. And I'm just going to stress the degrees here. So we have 3 times x to the second. X plus 5 implicitly is going to be to the first. And we have 3 minus 2x is raised to the third. So we have, in the case of the zeros. Okay. All right, so you got 0, negative 5, as well as 3 halves. And in terms of what we have with the corresponding multiplicities, again, 0 originates from the first factor where the variable is squared. So 0 has a multiplicity of 2. Negative 5 comes from x plus 5, which is raised to the first. So negative 5 has a multiplicity of 1. And for 3 halves, this comes from this factor, which is raised to the third power. So we have a multiplicity of 3. And in terms of whether the graph crosses or touches the x-axis, okay, so 0 has an even multiplicity. Okay, so it's going to touch at x is equal to 0. and with -5 and 3 halves with odd multiplicities. It'll be at those locations that we're going to have f of x to cross the x-axis. So crossing at x equal to -5 and to cross at x is equal to 3 halves. And in terms of what we have with the y-intercept, okay, so again we have with this function, okay, we have with the y-intercept, so I have 0y, and the y-intercept would be y, the value of y whenever x is set to 0. And this is going to be automatic, okay, because here we have 3 times the square of 0, which is going to go to 0. 0 plus 5 is 5. 3 minus 0 is going to be 3. And it really doesn't matter what the follow-through will be, because 0 squared is 0, and that's just going to cancel everything out. Okay, so you have 3 times 0, and any number, regardless of how large or small it is, once it is multiplied by 0, you will have the product to end up at 0. So we have, for the y-intercept, this will be located at the origin. All right, and so we have, looking at sketching the graph of f of x. So just looking at the characteristics. Again, I'm just sketching, okay, not exactly drawing according to scale. So the x and the y-axis, and again for the zeros, I have 0, -5, and 3 halves. Okay, so 3 halves will be right between 1 and 2. Okay, and just providing points here. Okay, so you have -5. You also have at 0. You also have at 3 halves. And for the behavior of the graph, so at -5, okay, now the graph is going to cross. At the origin, the graph is going to touch, and at x equals 3 halves, the graph is going to cross. And now, with the end behavior, again, you have moving down both to the left and to the right. Okay, and so, yes, you have the end behavior. So to the left, okay, starting from x equal to -5, so you have the graph to fall to the left, and with from the rightmost 0, namely in this case 3 halves, again the graph is going to be moving downward, so you have again falling to the left and falling to the right, or down to the left, down to the right. And just for the rest of the activity, okay, so kind of doing what they call a bit of the interpolating. So we have reading in order from left to right. Okay, so you have going from below the x-axis, and once we get to -5, okay, now the graph is going to cross, come to a threshold, and it's going to start to descend. And once we get to the origin, okay, now the graph is going to touch, then it's going to rise again, and then it's going to descend. And once we get to x is equal to 3 halves, the graph is going to cross, and the motion is going to remain continuously downward. Okay, so this will be, like, again, I'm not drawing according to scale, but this will essentially be the dynamic for what we have in illustrating how f of x is going to behave. So you have falling at both ends in accordance with the end behavior, and also we have the manner upon which the graph moves with respect to the zeros. All right, now for what we have in the case of number 3, and we have it's kind of going back to what we have with polynomial division. And so what I'm going to do here, then we'll just add a page. We've got this somewhere. Oh, it's not doing what I want it to. All right, so we'll go back to the to the previous page. Okay, so we got for the case in number 3. Okay, so we got. I don't know what I'll do here. I'll just drag this on down. Okay, so we're looking for the quotient and the remainder. And for what we have in number 3, okay, so we have the divisor, okay, at 2x plus 4. And we have with the dividend, okay, so we have 4x to the 4th plus 2x squared plus 6x. Now, where I can, I normally like to go with synthetic division, but since I have a coefficient other than 1 in front of the x, okay, I would have to take some extra steps to perform the synthetic division. Okay, so we're just going to stick with the line division on this one. Okay, so we have so we have 4x to the 4th, and from the dividend, okay, now we do not have a cubic term, so I'm going to use 0 for placeholder purposes to signify that we have a missing cubic term. Now we have plus 2x squared, then I have followed by 6x, and I want the dividend to close out with a constant, okay, and so we had to apply another 0. Okay, and looking at the long division, so you have 2x into 4x to the 4th. So this will go 2x cubed times, and distributing 2x cubed over 2x becomes 4x to the 4th. 2x cubed over 4 becomes 8x cubed. And looking at subtracting, okay, so 4x to the 4th goes out, and I have 0 minus 8x cubed, so I'm going to have a negative 8x cubed. Now the lower degree terms that follow have not been touched yet, so I'm just going to bring these on down. And we have 2x into negative 8x cubed. This is going to be negative 4x squared. And distributing, so we have negative 8x cubed. And we have minus 16x squared. And again, applying subtraction. Okay, so we have negative 8x cubed plus 8x cubed will go out. And we have 2x squared, and what's going to be plus 16x squared. This will be 18x squared. We have plus 6x plus 0, and then we have 2x into 18x squared is going to be at 9x. Then we have distributing, so we have 18x squared plus 36x. And applying subtraction, okay, so you have 6x minus 36x, so we have negative 30x. Yeah, plus 0, and once more, okay, so I'm going from taking 2x into 4x to the 4th, then negative 8x cubed, then 18x squared, and finally it will go into negative 30x, negative 15 times. And distributing, we want to have negative 30x minus 60. and applying the subtraction. Yep, once more. Okay, so we have what's going to be 0 plus 60. So this will be 60. And for what we will have here is that which we have at the top. Okay, that is going to be the quotient. And with 60, I cannot take 2x directly into 60. And so that number 60, okay, that is going to be the remainder. Right. Now, so number 3, okay, I looked at line division. Now for number 4, okay, now we're crossing over to synthetic division. And in this one, okay, we have the divisor at x minus 5, and we have the dividend, okay, we have 2x cubed plus 2x minus 9. Okay, now I'm going to use synthetic division, I am at liberty to go ahead and convert in terms of synthetic division, since we have the expression to be first order in x, and since I have the leading term to be x, no coefficient other than 1 in front of it. Okay, again we have with the dividend, okay, we have 2x cubed, and we have a missing x squared term, and then we have plus 2x and a negative 9. So I only needed a 0 placeholder in the dividend for the x squared position. Now for the synthetic division, okay, if I establish the 0 from the divisor, so I'm going to have that x is equal to 5. And setting up things in accordance with synthetic division. And again, I'm going to use like Alex's notation for the synthetic division setup. I kind of like the elbow formation, but I guess to each their own. Okay, so we have, so we got 2 for x cubed, 0 for x squared, and we have 2 for the first order in x, and we have negative 9 at the end. So looking at synthetic division, again, we have column by column addition. And with the leading coefficient of the dividend at 2, I'm going to bring this down, and that's going to be also the leading coefficient of the quotient. And here we have 5 times 2 is 10. Shifting over, 0 plus 10 is 10. 5 times 2, okay, was 10. After adding 10, we got now 5 times 10 is 50. 2 plus 50 is 52. And 5 times 52 is going to be 260. And negative 9 plus 260 is going to be at 251. And so you're going to have the remainder. Okay, that is going to be at 251. And as for the quotient, okay, that's going to be 2x squared plus 10x plus 52. And just for what we have in the expanded form, where we have the quotient along with the divisor and the quotient and the remainder over the divisor layout. So we have a 2x cubed plus 2x minus 9 all over x minus 5. Again, so that's going to be equal to the quotient. So you have 2x squared plus 10x plus 52. And then we'll have plus, again we have 251 all over x minus 5. So again, you have the quotient plus the remainder over the divisor. So that'll be the complete layout in the case of problem number 4. And for what we have in number 5, and it says to use the remainder theorem to find the quotient and remainder of P of 2 given that p of x is equal to 5x cubed minus 4x plus 7. So again, we have p of x, so we have 5x cubed minus 4x plus 7, and we have, again, so we have p of 2 Okay, now that 2, to which we have p of 2, okay, that is going to be signaling that the divisor is going to be at x minus 2. And looking at division, and we have just in the setup, so I have the divisor at x minus 2. Now the dividend, okay, that's going to be the terms that define p of x. So I have 5x cubed, and notice I do not have an x squared term, so I have another 0 placeholder to apply, and then we have minus 4x plus 7. Okay, so you have x minus 2 equal to 0. We have the x's equal to 2. So just putting what I have along the lines of synthetic division. Okay, so I got, again, 2 is the 0. Again, we have with the coefficients of the dividend. Okay, so all places represented, so you have 5 in the cube, 0 for the square, negative 4 for the first order in x, and then finally we have the constant 7. Okay. And so just taking what we have now. Okay, so again, the leading coefficient in the dividend is also going to be the leading coefficient in the immediate quotient. So 5 is brought down, and we have 2 times 5 is 10, 0 plus 10 is 10, 2 times 10 is 20, negative 4 plus 20, okay, it's going to be at 16, 2 times 16 is 32, and 7 plus 32, okay, it's going to be at 39. Okay, and so we have for the outcomes. Okay, so we want to have the remainder. Okay, now the remainder would be like your p of 2, which is going to be 39. And as for the 5, the 10, and the 16, okay, we're going to have for the quotient, okay, we're going to have 5x squared plus 10x plus 16. If I did the full display, you would have like 5x squared plus 10x plus 16 plus 39 all over x minus 2. And I just want to mention, okay, so I had to use the log or the synthetic division to get the quotient part. And I just want to mention just with the remainder theorem. Yes, I had stressed that r is equal to p of 2. And guess what? For the function value, whenever I have the 0 of the divisor as the input for this function, okay, so you got p of 2, you have equal to 5 times the cube of 2, and I have minus 4 times 2, followed by the addition of 7. So 2 cubed is 8. And we have minus 4 times 2 is negative 8. And we have plus 7. 5 times 8 is 40. Negative 8 plus 7 is going to be negative 1. And guess what? 40 minus 1 comes out to 39. Okay, so the function value, the remainder theorem in the standalone operation, okay, it's going to get to just the remainder. And if you notice, okay, so these are going to end up being the same. And for what we have in the case of the next item, and we have concerning, I believe, the factor theorem. Yeah, it says use the factor theorem to determine if x plus 2 is a factor of p of x equals x cubed minus 2x squared minus 3x plus 10. Okay, and okay, so we have so you got with the divisor. Okay, so you have x plus 2. And again, we're taking into p of x, okay, where we have the dividend, again, at x cubed minus 2x squared minus 3x plus 10. Okay, so everything in the degree and x in the dividend from third to second to first order to the constant, okay, we have already established. So no zero placeholders were needed. Okay. And so for what we have in this problem, let's look at translating from the long division setup to what we have in synthetic division. So for x plus 2, if x plus 2 is equal to 0, so we have that x is equal to negative 2. So you have negative 2, and I have 1x cubed minus 2x squared. Got minus 3x. And we have plus 10. Okay, so you have with this synthetic division. Okay, so again, the leading coefficient of the dividend will be that also of the quotient. Here we have negative 2 times 1 is negative 2. Negative 2 plus negative 2 is going to be negative 4. Negative 2 times negative 4 is going to be a positive 8. Negative 3 plus 8 is going to be a positive 5. Negative 2 times 5 is negative 10. And 10 plus negative 10 is going to be 0. And it's going to follow that the remainder is going to be equal to p of the 0 of the divisor, which is negative 2. And that is equal to 0. And again, the problem did not ask for the quotient, but that would be x squared minus 4x plus 5. Okay, so you got the remainder at 0. And in terms of the fill-in-the-blank portion and the yes or no item, okay, so it's going to follow that we have here. So we have p of negative 2 is equal to 0. And because the remainder is equal to 0, it's going to signal that x plus 2 is a factor. If the remainder had been non-zero, then x plus 2 would not have been a factor. And so just looking at what we have now with the inequalities. So you have with number 7, okay, so you have a polynomial inequality. Okay, so you have x squared minus 4x is less than or equal to 12. And if I rewrite this in terms of a comparison to 0 inequality, so I have x squared minus 4x minus 12 is less than or equal to 0. Okay, so we have a polynomial function. Okay, and just the general format. Okay, we have f of x is less than or equal to 0. And just looking for the zeros of this particular polynomial. So if I set x squared minus 4x minus 12 equal to 0, we have with the factors. Okay, so we have x minus 6 and x plus 2. equal to 0, and with these, okay, so if x minus 6 is the 0 factor, okay, we're going to have the x is equal to 6. And for x plus 2, if that is equal to 0, we're going to have that x is equal to negative 2. Okay, so again, we have in the setup, okay, we have the f of x equals x squared minus 4x minus 12. And we have with the zeros, again, we have 6 and negative 2. And we don't have to worry about whether the zeros are in the domain or not, because with polynomial functions, where everything is given in direct fashion, no even root radical, no fraction, okay, we have the domain to be the set of all real numbers. And just setting up a table, okay, of intervals. And we have revolved about the zeros. Okay, so with negative 2 as the smaller of the zeros, we have the smallest values of x to be those which are less than negative 2. And then we have next in line, you have those values of x greater than negative 2 and less than 6. And then we finally have those values of x which will be greater than 6. And just, again, in the formation, okay, so we have upon separating into distinct subinterval sections, and we're going to test each of these out. Okay, just kind of taking, again, test input values, where each value tested will belong to the corresponding interval section immediately above. Okay, so for our tested values x, okay, so anything less than negative 2, we can go with minus 3. Between negative 2 and 6, we can go with 0. Anything greater than 6, okay, 7 is a possible choice. And looking at testing out the value of the function, and the function being where f of x is equal to x squared minus 4x minus 12. And we have with f of negative 3. Okay, so we have negative 3 squared minus 4 times negative 3 minus 12. Now the square of negative 3 is 9. Negative 4 times negative 3 is going to be plus 12. We have minus 12. And so we have for the output here, that is going to be a positive 9. In the case of f of 0, okay, the variable terms will be negligible, and right away, f of 0 is going to be negative 12. In the case of f of 7, okay, so you got 7 squared minus 4 times 7 minus 12. 7 squared is 49. Negative 4 times 7 is negative 28. Here we have minus 12. And we're going to have for the output here, that is also going to be a positive 9. And so in the case of the sign value of f of x at each stage, okay, it's going to turn out that for the first and the last subinterval sections, okay, those can be positive, whereas in the second, okay, that is going to be negative. Okay, so we have here, again, so you have positive for the first. So we have the f of x is greater than 0, and again, in the middle, we have the f of x is less than 0, and for the last, we have a positive, whereupon we have the f of x is greater than 0. Okay, so again, with our original inequality, okay, we had x squared minus 4x is less than or equal to 12, and rewriting as a comparison to zero inequality. We have it to be such that the nature of it is going to be where the function is less than or equal to 0. And this will be in the same direction as where f of x is less than 0. And that part has the limit values -2 and 6. And since we have the inequality in this problem to include the equal sign, okay, you have brackets to be involved. And since both -2 and 6 will set the expression or create the equal part in the inequality, -2 and 6 will be included in the solution where we're going to have brackets for the enclosures. Okay, so this will be your interval solution for this problem. And we have, in the case of the next inequality, okay, so you have already established as a comparison to 0 item. And here we have x squared minus 4x over x plus 5 is greater than or equal to 0. And in this one, so you have x squared minus 4x over x plus 5, okay, is greater than or equal to 0. So you already have, so you already have this expression compared to 0. And again, so you could write this as f of x or r of x is greater than or equal to 0. And looking at establishing the zeros, okay, so we have for x squared minus 4x, if I set this equal to 0, okay, so you have applying the factoring. Okay, so you have from x, we have x equal to 0, and with x minus 4 equal to 0, we have the x is equal to 4. And with the denominator expression, we have x plus 5. And again, the 0 of this is going to be x is equal to -5. Okay, so we have in the setup, so we have for r of x again, we have x squared minus 4x all over x plus 5. And we have with the zeros. Okay, so you have 0 and 4. Those stem from the numerator. So those items will be in the denominator. Again, you can have a 0 numerator, but not a 0 denominator. So both 0 and 4 we have in the domain. But in the case of -5, this stems from x plus 5, which is situated in the denominator. And if I have x at -5, the whole rational function will become undefined. Again, since you cannot divide by 0. And so we have working with this function and setting up intervals, okay, about the zeros. Okay, so you have 3 zeros. Okay, so we have a pretty wide array of subinterval sections. And out of 0, 4, and -5, okay, we have the smallest value among the zeros is -5. So the smallest set of values in x will be those values x less than -5. Then we have following, we have between -5 and 0, and bypassing 0. So we have those values between but not including 0 and 4. And we have with 4 as the highest of the zeros. We have at the highest end for the values in x, it will be those values which will be greater than 4. Okay, so you have from -infinity to -5, -5 to 0, 0 to 4, and then we have 4 on out to infinity. And looking at establishing tested values in the set. Okay. Okay, so for what we have in the for the inputs that can be chosen. Okay, so for anything less than -5, okay, we have -6 is a possibility. Between -5 and 0, as much as I like to choose 0, I cannot have that choice. So I'll just go with -1. Likewise here, I cannot choose 0, so I'll just go with 1. And anything greater than 4, I'll just go with the number 5. And for the function, once again, okay, so we have r of x equal to x squared minus 4x over x plus 5. Okay, so we have in the case of r of -6, okay, so you have -6 squared is going to make 36. -4 times -6 is going to be a positive 24. -6 plus 5 is -1. So you got 60 over -1, and so that will come out to minus 60. Now for r of -1, okay, so you have -1 squared is 1. -4 times -1 is going to be a positive 4. -1 plus 5 is 4. So that particular output is going to be 5/4. Now for r of 1, yeah, 1 squared is 1. -4 times 1 is -4. 1 plus 5 is 6. So we got -3/6, and that is reducible to -1/2. Okay, so you have a negative sign value. And the reduction, like in the case of simplifying fractions, it's not critical. The main thing is the sign value. And for what we have in the case of r of 5, okay, so you have 5 squared is 25. -4 times 5 is -20. 5 plus 5 is 10. Now the difference we have at 5/10. Again, that's already going to be a positive fraction. And just for the reduced form, okay, this is going to be a plus 1/2. And for what we have in the case of the sign of r of x, and we have in the first section, case they have, looks like we'll be alternating between negatives and positives. So you have a negative in the first, so we have r of x is less than 0. Next we have a positive, whereupon we have that r of x is greater than 0. Next we have a negative, where we have the r of x is less than 0. And for the last we have a positive, whereupon we have r of x is greater than 0. And just taking what we have with the inequality, okay, so we start out with, again, x squared minus 4x over x plus 5 is greater than or equal to 0. And again, the format is where we have r of x is greater than or equal to 0. So we're going to have this to be in the same direction as where r of x is greater than 0. And for what we will have in the case of the solution. Okay, so just adopting the limit values from where r of x is greater than 0. So we have between -5 and 0. Now, so I have between 4 and infinity. Now, for the enclosures, okay, now infinities are boundless, so infinity stays in the parenthesis. Now, with an equal sign, there could be potentially at least a bracket, though not a guarantee. Now, and this will be contingent upon whether the limits are each going to be in the domain or not. Now, for -5, again, that creates a zero denominator, so that is not in the domain. So -5 stays in the parentheses. Now, for 0 and 4, those create the equal to 0 part. And so 0 and 4 are both in the domain. And so we can place a bracket around 0 as well as 4. Okay, so for your solution set, this is what we have here, where we have a set of values x such that -5 is less than x, is less than or equal to 0, or x is greater than or equal to 4. All right, now in the case of what we have in number 9, okay, so we have yet another comparison to 0 inequality, and this is I think somewhat simpler ratio. And in this one case, so you have just x plus 2 over x minus 6, again, is greater than or equal to 0. Yeah, so this is already laid out in comparison to 0 terms. And so this is going to be in the format, again, where we have r of x is greater than or equal to 0. And it's going to mention, okay, just going ahead and identifying the components. We have the r of x is equal to x plus 2 over x minus 6. Now for the zeros, okay, now for x plus 2, we're going to have -2, and -2 will set the function equal to 0 since the factor is exclusively in the numerator. And so that one is going to be in the domain. On the other hand, okay, we have with x minus 6, okay, the 0 value is 6, and that value would create a 0 denominator. Okay, so 6 is not in the domain. And so just setting up, again, a table of intervals. Okay, so you have with -2 as the smaller of the zeros. Okay, so you have the smallest values of x, so it'll be those values less than -2. Then you have those values between but not including -2 and 6. And then you have those values of x which will be greater than 6. And just looking at what we have with our inputs that we can apply. Okay, so anything less than -2, we can go with -3. Between -2 and 6, I can once again apply 0, and anything greater than 6, okay, we can go with the number 7. And again, we have with r of x equal to x plus 2 over x minus 6. Okay, so we have with r of -3. Okay, so you have -3 plus 2 is -1. -3 minus 6 is -9. Okay, so we'll have negatives to cancel. So the output is going to be positive 1/9. And for r of 0, okay, so you have 2 over -6. And that reduces to -1/3. As for R of 7, okay, so you have 7 plus 2 is 9. 9 minus 6 is 1. Okay, so that's going to be a positive 9. And in the case of the sign of R of x, so we have for the first subinterval, okay, so that is going to be a positive. So we have the R of x is greater than 0. Then we have next, we have a negative. So we have R of x is less than 0. Then for the last, we have a positive, whereupon R of x is greater than 0. Okay. And just going back to our original inequality. Let's see if I copied that. No, I didn't. Okay, so we have in the setup, okay, so you have x plus 2 over x minus 6 is greater than or equal to 0, and this will be in the format of R of x is greater than or equal to 0. And so we'll have in the case of the solution. Okay, so you have going in the same direction as R of x is greater than 0, so we are involving the limit values of negative infinity and negative 2, as well as the values 6 and infinity. And once again, okay, infinities are boundless, so you have those in parentheses. Now for negative 2 and 6, now negative 2, that creates the equal parts of the inequality, and negative 2 being in the domain, so that is going to be in the bracket. As for 6, however, that just creates an undefined scenario for the rational expression. Okay, we already said that 6 is not in the domain, so that is going to be in the parenthesis. Okay, so that'll be your interval solution for what we have in this problem. And we have, now in the case of number 10, okay, so we have a comparison inequality, okay, where we have the comparison between ratios. And we have, for this one, it's a little bit long-winded in looking for the solution. Okay, so again, we have x over x plus 6 is greater than or equal to 1 over x. Okay, and I can convert this as a comparison to 0 inequality. So I can just move the 1 over x over. And so we have x over x plus 6 minus 1 over x is greater than or equal to 0. And I'm going to be looking at consolidating as a single expression. Okay, so I want to be able to combine these fractions into one. Now we have for the least common denominator, again, that's going to be x times the quantity of x plus 6. So I'm going to be raising both of these ratios in terms of the least common denominator. So we have with x over x plus 6. Now we have the x plus 6 factor, but missing the x. So I'm going to multiply the first ratio by 1 in the form of x over itself. Now we've got minus. Okay, now we've got 1 over x. And again, we had the role reversal. X is present, but missing is x plus 6. So I'm going to multiply that second ratio by 1 in the form of x plus 6 over itself. And we have in the follow through. Okay, so we have first ratio, we have x squared all over x times the quantity of x minus 6. And I'm putting the subtraction at bay right now. And we have with the second ratio, we have x plus 6 all over x times the quantity of x plus 6. So I have the same denominator for both of these and combining the numerator terms. Now x plus 6 from the second ratio, that's going to be affected by this subtraction preceding the ratio. And sort of narrowing this down. So we have x squared minus x minus 6 is over x times the quantity of x plus 6. And this trinomial at the top is factorable. And I'll just go ahead and write this in factored form. So I'm going to have x plus 2 times the quantity of x minus 3 is all over x times the quantity of x plus 6. Okay, so for what this is going to narrow down to, okay, is that we have x plus 2 times x minus 3 all over x times, okay, the quantity of x plus 6 is greater than or equal to 0. And again, this will be the form whereupon we have r of x is greater than or equal to 0. Okay, and so we have in establishing the zeros and all that and categorizing. Okay. Okay, so you're going to have here okay, so you have r of x is equal to okay, so I have this ratio of terms. Now for the zeros. Okay, so from x plus 2 I have negative 2. Okay, that's going to be in the domain. And from x minus 3 we have x equal to 3, and that just creates a 0 numerator value. Okay, that is also in the domain. But now for the other two zeros, okay, those will not be in the domain since the corresponding factors are situated in the denominator. And we have with x plus 6, I have x equal to negative 6. And again, we have not in the domain. And so in setting up our interval sections, okay, so you have 4 distinct zeros, and the least of these is going to be negative 6. So we're going to start out with values of x less than negative 6. Then we'll have those values of x between negative 6 and negative 2. You have those values of x between negative 2 and 0. We have those values between 0 and 3. And we have at the highest end, okay, we have those values of x which will be greater than 3. Okay, and just for the test values that we can apply. Okay, so for the first item, okay, so for anything that is less than -6, okay, I can go with -7. Between -6 and -2, I'll just go with -3. Between -2 and 0, if I still work with integers, I can only choose -1. And then between 0 and 3, I can go with 1. And anything greater than 3, I can just go with 4. Okay. And so we have okay, so after the selection of these input values, and we have applying to, again, our function r of x, and finding out what the output values are going to be. Okay, so for what we have in the case of r, okay, whenever x is at -7, okay, so you have -7 plus 2 is -5. -7 minus 3 is -10. Then we have -7. -7 plus 6 is -1. Now, you got 50 over 7. So just for the first output, this is going to be positive, where we have 50 over 7. For r of -3, so you got -3 plus 2 is -1. -3 minus 3 is -6. We've got -3. -3 plus 6 is +3. So we have 6 over -9, and that would reduce, again, reduction not critical, just get the sign value. So we have here -2/3. And for r of -1, -1 plus 2 is 1. -1 minus 3 is -4. You got -1, and -1 plus 6 is 5. So you got -4 over -5. So that is going to be a positive 4/5. And in the case of r of 1, okay, so I have 1 plus 2 is 3. 1 minus 3 is -2. And you got 1, and 1 plus 6 is 7. And so we have, for this output, we have -6/7. We have for r of 4, okay, so 4 plus 2 is 6. 4 minus 3 is 1. And you got 4. And 4 plus 6 is 10. Okay, so you got 6/40, and that is reducible to 3/20. Again, the key thing among the outputs is the sign value. So for the sign of r of x, okay, so we have for values of x less than negative 6, we have a positive output. So we have the r of x is greater than 0. Next we have a negative. So we have r of x is less than 0. Next we have a positive. So r of x is greater than 0. Next we have a negative. So we're in the pattern where we have alternating positive and negative values once again. Okay, and so for what we have, all in all, okay, so this inequality, again, as a comparison between x over x plus 6 and 1 over x, or x over x plus 6 is greater than or equal to 1 over x. And so for what we'll have in the solution, okay, so you have the format along the lines of r of x is greater than or equal to 0. You have in the solution, so you have, again, so you have involving the limits, negative infinity, negative 6, you also have negative 2, and 0. You also have 3 and infinity. And for the enclosures, okay, so you have parentheses around negative and positive infinity. Now in terms of the grouping symbols, for negative 6, negative 2, 0, and 3. Now negative 6, that one is not in the domain, so that cannot be bracketed. So negative 6 is in the parenthesis. Negative 2 creates the equal to 0 part, so negative 2 is in the domain, so that's going to be in the bracket. 0, again, like negative 6, is not in the domain, so that stays in the parenthesis. And then we have with 3, that is in the domain, and like negative 2, it sets the function equal to 0, and so 3 is going to be in the bracket. And so that would be your interval solution for that particular problem. So you have 3 subinterval sections in the solution, and we have only brackets around negative 2 and 3.